by default, Mike, you get to be the first. So very high level, what do you think is really taking shape, the NICE workshop, in terms of different areas that we're looking at? Are there things that you'd like to highlight? And then what we'll do is maybe like a 3 to 5 minute overview from all the members, and then we'll do a sort of a general discussion here and wrap up, fairly open-ended, so please.
Well, let's see. To me, looking at neural-inspired computing elements means drawing inspiration from neuroscience, and the elements meaning the principles that we see in the study of neuroscience as of the 2019. And so this is looking at what are the limitations and how do we go beyond the current state of the art, which is of course providing great value to the world, deep learning and these perceptron type of artificial neural network models, but these are limited by the fact that they're very old models of neural computation, and there's long lists of reasons why while we should be celebrating the progress that they're making and the value they're giving today, we can also recognize the limitations for continued advancement and living up to the increasing hype in this field. And we really, I think this community is all about looking for the source of that original inspiration, but based on modern understanding and how we can then adapt that into the systems that we can build today.
Okay, so I'm Winfried Wilge from IBM Research in Almaden, over in California. There are three things which puzzle me and thinking me quite a lot about this field. The first one is the, shall we say, unreasonable success of conventional machine learning. What I mean by that is the following. I'm a nuclear physicist by training, so I often think about this relationship. In the 40s, when people tried to understand why fission released so much energy, we created a thing called the liquid drop model. And it was a fit driven by physics, which involved a number, 5 parameters. And von Neumann didn't like that at all, having all these open parameters. He scoffed that with 4 parameters I can fit an elephant, and with 5 I can make wiggle its tail. And that reminds me very much what's going on in conventional machine learning. Let's say, sticking with an elephant, you have an image of an elephant. You fit it in some form, not in a curve, but in a pixel space, literally with millions of parameters being the weights of the synapses. And then you take another picture of an elephant and another one, 10,000, 50,000. And so you get a set of parameters, each for each picture of the elephant. And then you hope that out of this pile of parameters, you find some consistency, independent if the elephant looks at you as you see it from the side or is in the upper left corner of a picture. And then you do the same with cats, and you get another pile. And you expect that these fall into different clusters. It's unbelievable. I talked to some of what we're really talking about here is finding minima in a maybe million-dimensional space. And I talked to a few mathematicians about it and said, can one understand what's going on here? And basically shrugged their shoulders. So why the heck is it working so well? I don't get it. Okay, that's number one. Second, now, since we're all talking about devices to accelerate this conventional, surprisingly well-working machine learning, today we are focusing mostly on devices like phase change or resistive RAM, but they don't work all that well really in the sense what we need devices which the impedance can go up, it can go down in small step, controlled billions of times ideally, and none of them which we have today or work on really do that very well. And the fundamental reason is that we are moving atoms around in these devices. And I think that is probably a mistake. If we would move electrons around or maybe magnetic spin directions, things which are reproducible, then I think we have a better chance to build devices which do what we really want for this field. And the third topic which I'm puzzling about is the relationship to biological learning. In machine learning, we have a fixed topology, and we learn by fiddle with the weights, right? That's not what the brain does. The brain learns by forming new connections. But the three-dimensionality of a space is crucial, right? Let's assume this arm is the axon of one neuron, and this here is the dendrite of another neutron. When we are far in space, it works. Nothing interesting ever happens. But if we are close to another and there are coincident firings often enough, then quickly synapses form there, right? Such a picture makes only sense in three-dimensional space. I don't think it makes a lot of sense in two and totally impossible in one-dimensional. So I think when we want to build devices which are truly intelligent and which inspired by working from biology, which I think is a good guidance, when we need to eventually, years out from now, create such truly three-dimensional devices, we don't know how to do that, but I think that should be an interesting topic going forward.
So I was sitting here looking at the audience, and just out of curiosity, who has been to all 7 NICE workshops? 4, 5 people in here, and I think that's telling. You know, the very first couple of workshops that we did in Albuquerque, it's a very different field. I mean, the amount of progress that has happened over the past 7 years is amazing. And you know, I think the questions that both Mike and Winfried have asked, and I'm sure we're going to hear in a minute, I think are indicative of a maturity that our community is starting to have, and it's really starting to get some momentum. You know, 7 years ago, we were sitting around asking, why will anyone care about this? You know, we all knew, you know, I mean, I'm a neuroscientist by training, so it's like, oh yeah, the brain is awesome. The brain does all this great computation. We like to leverage it. But what is the killer app? What is the impact on the world? Well, we have that now. We see that every day in the newspaper with things that machine learning is doing, which is scratching the bare surface of where brain inspiration and neural approaches can go. I think all of us up here at least, and probably in the audience, really think that, you know, this is the start of something amazing. And so, you know, I think it's nice to reflect on how far we've come. We're no longer worried about what is a killer app. Can there be a single killer app for neural inspiration? I mean, deep learning in 1960s neuroscience has done that. We have 50 years of neuroscience since then that has shown amazing things about how the brain works. We have advances in electronics and devices that we can do amazing things if we bring it all together. And I think so. The question's not, is this the right thing to do, but rather, you know, how do we, you know, what are the best next steps? How do we bring this technology forward? You know, what is the right set of approaches? What are the software stacks and the first major impact outside of the deep learning universe that we can make and so forth. So I'm excited. It's, you know, every year it's like you can just feel the progress being made when you come to NICE. So I'm excited to hear kind of how far we've come since, you know, just a year ago in Portland. So.
Unfortunately, Brett has said the same things I wanted to say, so I will repeat him now. Biology is awesome, and we really should be very modest if we look at what the brain can do, and neuromorphic computing is about to bring this power to technology. And I'm still very optimistic that this is the next generation of computing. It will be the generation of computing that takes over from Turing-based systems you have now in the long term. But it's still a hen and an egg problem. And to solve this, this is our job. We have to create either the hen or the egg so that the other half can be completed. That means that, for example, theoreticians and modelers use what we give them to bring algorithms to the hardware or vice versa, we build hardware for the algorithms, but we have to close the loop between theory, algorithms, and the implementation, because what we have learned in the past that the numerical simulations do not bring it. And they lead the theoreticians on the wrong path. They lead them to the path of numerical precision, of repeatability, of exact devices, of software-based thinking, and that is just wrong, plain wrong. Nature does it totally opposite way. And we have to come with a model closer to nature to enable success in bringing the systems closer to nature.
So an advantage of coming towards the end is you get the idea of what people are saying. The disadvantage is
You have to repeat me.
they've already said it all. So my take on this is we've been thinking about neuromorphic technology in Manchester for 20 years now, and building systems for more than half of that. And most of that time, the primary goal has been to build machines that can contribute to understanding the brain by supporting large-scale brain models. So the focus has been understanding the brain. And quite independently, there's been this explosion in machine learning, which has a degree of bio-inspiration, but obviously less biological detail, based on older style continuous nets. And I think what's interesting is the strong sense of convergence that there now is between those two topics. So I don't think that neuromorphics is going to displace conventional machine learning. I think both have a lot to learn from the other. But we're still in the position that neuromorphics has no killer app. There's no compelling demonstration of the commercial viability of spiking neural networks at the moment. What there is, from where I sit, is much more evidence that that's not far off. And most of this is coming from advances in theory, a lot of that from partners in the Human Brain Project. And a lot of that is actually coming because they're looking at what conventional machine learning is doing and asking why do machine learning systems learn so much more effectively than anything we can build in spiking networks. And they are beginning to understand that. And there's beginning to be suggestions of mechanisms in spiking networks that deliver gradient descent learning, which is really quite close to error backpropagation. And as it's close, it's similarly effective. So I think we are seeing this convergence and this cross-fertilization, and I'm expecting something very interesting to emerge in that space, probably in the next 3 years before the end of HBP. Well, it's 4 years, isn't it? We have still 4 years.
Maybe only one.
Maybe only one. Well, yeah. Let's not get into HBP funding politics. That's a whole different story. So I sense that something interesting is imminent. We haven't got there yet. Now, neuromorphics is still entirely justifiable from its contribution to the brain science agenda. So we don't need commercial applications to justify our existence. On the other hand, it makes us a whole lot more significant if we can find that. And the evidence that this is beginning to happen is all over the place. I mean, there are interesting little startups popping up left, right, and center in the event-based neural network space. And people are putting money into this, presumably with the expectation of getting something out at the end. So I think we live in increasingly interesting times, but we aren't quite there yet.
Good morning, everyone. My name is Hemant Jagannathan from IBM Research in Albany. So first of all, on behalf of the host here, I'd like to welcome all of you to NICE 7. I'd like to begin with a question keying off with what Brad had started off with. How many of you are first-time attendees of the NICE conference? So I had a good suspicion, so it was a planted question, and as expected, you delivered. So that kind of answers how popular this topic has become from the 4 attendees of all NICE conferences to how many new first-timers we have for this conference. And as many of you, I'm also a first-time attendee of this conference. I'm a hardware person by training and for the past decade in IBM. And there are a lot of inspirations both in fiction and non-fiction which you can get in terms of what is AI, what is neural-inspired computing. But I had this basic question that I had, this problem that I had more questions than answers. So I looked around, and there was this conference, and I figured you may as well learn more by doing it. So here I am in front of you, and we are happy to present NICE 7 to you. Just keying off from all the speakers before me, we have a lot of great examples on machine learning, on training, and models which are being implemented for real-time applications. But you always wonder, are these the best which systems can do, and how do we do the most basic things like learning, inferring, and just adapting so well as human beings, and why are machines incapable of doing that today? And some of these fundamental characteristics are still baffling a lot of people, including myself and a lot of you here. I come from the other side, which is what materials, devices, hardware, architectures need to be built for these systems. Today, most systems are going to be based off of silicon. They're running with very conventional von Neumann-based computing and are using chips made from FETs. I'm trying to look at it from the other side of the tunnel while a lot of work is being done in the software, algorithms, and the neuroscience side to figure out the killer device, the killer material, which will replace MOSFETs for neural-inspired computing. And I'm sure a lot of you have a lot of ideas, both in across the stack, and we look forward to hearing from you during this conference.
So maybe just to kind of tie the conversation together, there is a very wide range, and this is something that we've been talking about at NICE from the very early beginnings. There's neuroscience, there is incredible amount of detail, biology there, and then there's theory, algorithms, and then there's software, devices, and then applications sort of connecting all back to saying, with all these things, we're going to then go feedback into either neuroscience or other applications, control systems, whatever they are. One thing in some of the workshops we've touched on was conventional systems are growing, they're sort of maturing to a certain level, and we're getting, again, better performance with the technology being improved on the microelectronic and optoelectronic device side of things. But is there a transition at some point where the impact that we might be able to get from these systems is bigger than what we would expect from conventional system improvements? So maybe if we go back and kind of any comments or any suggestions?
Steve, you seem to equate neuromorphic computing with spiking computing. I wouldn't do that, actually. I think one could buy neuromorphic systems. And I suspect if one asks anybody to define neuromorphic computing, we get quite different answers. But I would not set it has to be spiking to be neuromorphic.
I like spiking.
Okay.
But no, I mean, I think that kind of gets a little bit to what Murat was saying. I mean, there's some question about where is an advantage going to come from? Like, is there a theoretical advantage and so forth? And one of the things that I find appealing about spiking is that, it's not like a completely different model of computation like quantum is, but it is a different model of computation. There are theoretical reasons why it is that a spiking neuron is different than a logic gate, for instance. And so from a concrete point of view, it allows us to start asking those questions. If you just focus on spiking, you don't have to focus on spiking, but if you focus on spiking, you can start being very deliberate about asking the questions that Murat just asked. At what point do problems scale to a certain size where a spiking model, theoretical model of computation, shows advantages versus others? And I think you need to have that side. You need to have the hardware side that you talked about, and Hemant talked about. And you need to have the sort of theoretical computer science side, both of which really saying, okay, this is what we can do, and this is where we know that if we do this, it'll get better. And that's the thing we've missed in this field. We don't have a, if you build this, you will win story. And I think that, picking something, doing theoretical analyses on it, and focusing on that gives you a chance. Now, analog has a lot of advantages. There are other things we can do as well, so I don't want to dismiss that. I'm just saying spiking has a nice concrete angle to take.
Yeah, I think spikes get a disproportionate amount of attention. So yes, they're just one of many properties that we can look at as defining neuromorphic computing generally. On the other hand, in our program, we built a neuromorphic spiking neural network chip at Intel, and we're accumulating evidence that's quite enlightening because it tells us why, what we intuitively assume coming from the neuroscience, why spikes are actually efficient. And we can see that in how the computation is playing out. And indeed, when rigorously benchmarked compared to conventional systems, we see orders of magnitude gains. And some of that is from the spiking, some of it is from other properties of the neuromorphic systems, but pretty indisputably, spikes do have their niche. It's just a question of how broad is that and what is the actual real world value that you can extract from that in real applications.
I would not put them in that strong opposition as well, because if you look at a biological system, as long as you have a stable rate, even as you can have non-spike information transmitted by the spikes, and if you start to deviate from definable rates, then you have spike-based systems, or there's a smooth transition. It's like Newton mechanics to relativistic mechanics. It depends on how close you look and what use of the system. The bigger problem is the training part. I think the moment most of the people hope that spikes give them the possibility to do local learning in the system because they carry more temporal information, as a correlation information, that the rates alone do not, but the question is still open. So both might happen.
So I better answer about spikes. I like spikes. And I like spikes because I'm a computer engineer, and spikes make possible the construction of very large-scale neural systems. I don't know how I would do the communication at the scale of the Spinnaker machine if it were not the fact that spikes give me a convenient, quite digital communication model. Now, you can call them spikes. I generalize them to events. So they don't have to be physically signals that go up and down. To me, a spike is a pure asynchronous impulse. It's a unit impulse that's propagated from one neuron to many others, and that's very convenient for building machines. And of course, it's not the only communication process in the brain. There are neuromodulators. There's, the brain is a soup of complex chemistry, and communication is happening through many mechanisms in addition to spikes. But spikes in the mammalian brain are the primary real-time communication system, and therefore they're very important. I don't think they're secondary. Now, if you look at why the biology spikes, then the Lachlan-Sterling book, I think, gives the best analysis of the advantages of spikes in biology, and it's the advantage only cuts in when the communication distance is beyond about a millimeter or two, I think, because very small creatures do not spike; they use analog communication. But once you get above a millimeter or two with the biological technology, which is different from our electronic technology, then spikes become more efficient at communicating information.
But this is exactly the important point. In our brains, we have a lot of analog communication within the neurons. And so it might be just a point that from energy efficiency for short distances, you use analog, for long distances, you use spikes. And nothing else, maybe.
So maybe one more comment to bring into that conversation in terms of importance of time, either real time or simulated faster time. And again, in some of the projects and programs, it's been one of the key parameters. I think the way neural systems represent information is very critically tied to notion of time in terms of being able to sequence events, being able to encode information, but both, again, in spatial coordinates and also in time. So maybe to kind of move that conversation a little bit further, what is that? Is there a critical thing there in your mind? And also, if that's being done in other systems in a maybe not so realistic way, is there potentially a way where that's really the big advantage for these systems?
So I think that's an important. So I'll say from the neuroscience point of view, the brain functions at many different timescales. So right now we have synaptic transmission occurring at millisecond timescales in all of our brains. We have learning at seconds and minutes timescales. We have modulation at minutes and hours timescales. We have other forms of plasticity, like Winfried was talking about, where you have synaptogenesis and neurogenesis at days and weeks timescales. So, there's a tendency to think about, because we've been in this sort of serial von Neumann way of thinking of computing, where it's like, okay, I have a clock, and my instructions go dot, 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 right? Well, the brain is doing all of it at all these different time scales, at all these different spatial scales simultaneously. And so it's a completely different approach to computing, where you have, different aspects of the computation occurring at orders of magnitude different time scales and spatial scales. And we just don't have a way of thinking about that as a computing process. I'm absolutely convinced that the hardware that everyone else up here is doing, it's not me, that all the hardware that's being produced by this community can be leveraged in this way. I mean, not all of it has modulation and neurogenesis and so forth, but once you get into some of these spiking regimes and learning chips like Loihi and so forth, we can start having computation occurring at multiple time scales simultaneously. We just don't know how. We don't have, from an algorithm development point of view, other than the brain as an inspiration, I don't even know where to start looking at that. It's a completely different approach. So the brain does it. We need to learn more about how the brain does it. We need to tap into that. But I actually think that this is a case where the sort of multiple timescales, the hardware is ahead. Like, y'all have the tools. I mean, we could do it on Spinnaker. We could do it on Loihi. We could do it on brain scales. I think it's just a matter of how do we start doing it.
Yeah, exactly. We have to look at the brain as a dynamical system, which loops acting on all different timescales simultaneously, and that's what I meant with the problem of the prejudice the digital modeling gives, because it is totally opposite from Turing computing, and if you think sequentially, you are just thinking wrongly.
Yeah.
I got to say something in defence of Mr. Turing. I think he did quite a good job, and his most important result from the 30s was about the universality of computation, and that universality includes the ability to model everything that's being discussed today. Okay, so it is still the most powerful computing model available to us, and I'm going to disagree with my learned friend Johannes here. I do not think neuromorphic systems will replace Turing computing. I think they will complement it. I think Turing computing is with us for as far as I can see into the future. It has some very nice properties which are quite different from the biological systems, such as consistently getting the same answer. And 90% of my computer science colleagues see that as the first requirement of a computer system, is that you get the same answer every time you run the same program with the same data. And neuromorphic systems do not do that. But so.
Some Turing systems don't.
Yes, I agree. The caveats, but no, I mean, we're not here to see an end to Turing computing. I don't think that will happen.
in fact, I have to agree totally to Steve because he's always right. And this afternoon, I will exactly show in my talk what he said. I was trying to be a little bit more provocative before and talking about let's say, the machine learning part of the future computing, not the banking part.
So if you look at Turing and von Neumann, I was reading some of von Neumann's work. They were talking about the same things we're talking about here. Von Neumann's last work was The Computer in the Brain, which he was unfinished. He didn't finish it. But I think he would, reading into von Neumann, I think he would love this meeting, right? I think he wanted to go down a path towards brain-inspired, parallel thinking, not just the serial von Neumann machine approach that I think that has dominated computing for 70 years for good reason. So I don't know. I think the pioneers of computing probably would be attendees of NICE.
Just to kind of sum up what Johannes and Brad said, I think there are systems which you must have for certain aspects. You don't want to, at least in today's state, a neuromorphic computer in your backing system, thinking about how much bank balance you have. You want to know a number and make sure that that number is exact and repeatable. But there are systems where obviously you would prefer to have neuromorphic systems to kind of augment and supplement the current Turing system. So I agree with Steve that Mr. Turing did a good job, and it's our job now to kind of supplement it with neuromorphic systems to a point where there may be a point where it may overtake, but I don't see that happening in the near future.
So, any comments? So maybe just one comment to add to that. We've had similar discussions in earlier workshops too, saying, well, is it replacement or is it supplement? And I think again, in certain applications, it might be possible to just have one type only. It doesn't make sense to try to do the other type of computing approach. But again, I think as some of the robotic systems or sort of the self-driving or self-flying systems that people are really looking to bring to bear, you might, again, even those systems too, you might want to have a system as maybe a fail-safe that just goes back to a rule-based scenario versus another one that's maybe a little bit more open and behaves more like a biological system. And I think based on some of the application requirements, those are going to get settled as systems evolve. So Brad, did you have a comment? So with that, let's thank the or Mike.
Well,
Sure.
I was just going to agree with you that there's nothing more flexible and programmable than the von Neumann model, and given that to get efficiency with neuromorphic models, you have to go to a very fixed function, optimized design. It's at odds with our need in computing to create flexible, programmable devices that can be used across a wide range of applications. So from purely a practical perspective, we will definitely have hybrid systems in any commercial deployment of neuromorphic technology. We have 3 von Neumann CPUs in our Loihi chip. Inside it, right? Let alone a host that would sit next to it. So I think, yeah, there's no debate that von Neumann is here to stay and sees a lot of future, even in its own innovation track. So,
Thank you. So,
yeah.
so with that, let's go ahead and thank the committee members.